Okay, you're welcome to another physics class, another physics lesson. In the last lesson, we started equilibrium of force, and in this lesson, we're going to be looking at a continuation of equilibrium of force. We said in the last lesson that equilibrium of force has to do with balancing of forces acting on an object or balancing of forces acting at a point. So now we're going to look at an extension of the equilibrium of the forces acting on an object. We'll start with what we call the moment of a force. The moment of a force about a point is the turning effect of the force about that point. It is equal to the product of the force and the perpendicular distance of its line of action. That means that when we talk of moment, we are talking of a force that is acting on an object, causing the object to rotate or go round. Like the example we have now, the force, as you can see, the direction of the point of application of the force on the handle of this object causes it to go round, to rotate at a particular point. So if the force causes the object to rotate, if it causes a turning effect on the object, it is called moment, which is the product of the force and the perpendicular distance to the line of action of the force. What do we mean by perpendicular distance? Look at the examples above. Look at the direction of the force. Now the direction of the force, let's use the spanner for instance. You see D, the place labeled D or the hammer, that distance is the perpendicular distance to the line of the force. In this case, the force is acting downwards from the diagram above. That downward force times the perpendicular distance is what we'll describe as moment. Hence, it is mathematically represented as force times perpendicular distance. So it is only termed or called moment if it has a turning effect on the object or the point to which it is applied. When we say turning effect, if it causes that point or the object to rotate, that is when we say it is the moment of a force. And then we'll go to the principle of moment. So this principle states that if a body is in equilibrium, then the sum of the clockwise moment about any point on the body is equal to the sum of the anticlockwise moment about the same point. When we say clockwise and anticlockwise, just as we have explained that when we talk of moment, we're talking of the turning effect of a force on an object or at a point. The example above explains clockwise. If it is turning in the direction of the second hand of the clock, then it is said to be clockwise. If it is going in the opposite direction, it is anti-clockwise. So the principle of moment is saying that this clockwise moment acting on one end of the bar, taken as example, has to be equal to the anti-clockwise moment acting on the other end for the object to be in equilibrium. This is also another example of the principle of moment. Remember, we said moment is represented mathematically as the force times the perpendicular distance. Hence, you have that force A times perpendicular distance A, which is from the line of action of the force to the pivot, is equal to force B times perpendicular distance B. That means that force B and distance B is the moment at the point B, and then force A and distance A is the moment at the point A. So for the principle of moment to be obeyed, it means that for an object to be in equilibrium, the anti-clockwise moment must be equal to the clockwise moment acting on the object. This is also another example. The size of the man in this case can still balance the size of the boy because of the perpendicular distance ratio between the clockwise and anti-clockwise moment acting on it, on the bar. And then we go to couple. We say couple are two parallel forces of equal magnitude acting in opposite direction and separated by a distance. The magnitude of a couple is calculated by multiplying the magnitude of force by the distance between them. What do we mean by couple? We'll see examples in a bit. Okay, now let's take the tap for instance. When two forces are acting at a point and they are causing a turning effect, two equal forces are acting at a point in opposite directions and they are causing a turning effect on that point or on that object, just like the handle of the tap. When you turn it, the two forces applied is known as couple. Even the steering in the example above, this is an example. Look at the circle on the left. The two forces act at the same time and are of the same magnitude, causing the object or the point to turn or to rotate, causing a turning effect. Those two forces are called couple. Now, a couple is calculated by picking one of the force. Since they are the same, pick one of the force and multiply it by the distance between the two forces. That's how you calculate the couple. And now we go to conditions of equilibrium under the action of parallel coplanar forces. The first one, we say the algebraic sum of the forces acting on the body in any given direction must be zero. The algebraic sum of the forces, that means the examples we gave just now, the forces going up, the forces coming down, the forces in opposite direction, if you add them together, they have to give you zero. That's what it means. And then the second one, the algebraic sum of the moments about any point must be zero. This is an example. Now, F1 and F, according to the first law, F1 and F2 has to be equal to N, which is the normal reaction in this case. So that if I am adding them, F1 and F2 and N, I am supposed to get zero. Why am I getting zero? Because since they are in opposite direction, one direction will take the positive sign and the other direction will take the negative sign. Force is a vector. So we're looking at that. And then the moment also should be equal to zero, such that maybe the clockwise will take the positive and then the anti-clockwise moment will take the negative. So if I add them together, I am supposed to get zero. Now, conditions of equilibrium of non-parallel coplanar forces, which is the vector sum of all the forces acting on the body must be zero, and then the algebraic sum of the moment of all the forces about any axis perpendicular to the plane of the force must be zero. It's similar to the other one, but the difference here is that the forces are not parallel. When we say parallel, look at the example we have. In the former one, when we're talking of parallel forces, we had forces going up and forces coming down, straight parallel forces. But in this case, they are inclined. Now, when we say vector sum, we are saying that you are resolving this force to the vertical so that it can face up. I'm sure you know what that means. We have done it in vectors. And then you are resolving it. If you see the two diagrams, one is at an angle, one is straight and down, because it has been resolved to vertical forces that are parallel. So those two forces algebraically should cancel each other out when you add them and give zero. Now, conditions of equilibrium under the action of three forces. The first one says the three forces must lie in a plane. 2, their line of action must intersect in a common point, and the vectors representing the three forces can be arranged to form a closed triangle with sides respectively parallel to the direction and proportional in length to the magnitude of the force. This is in simple relation to what we learned earlier when we were talking of triangle of forces that we did in the previous module. If three forces are acting at a point, then they should be able to, and they're acting at a point and they are at equilibrium. That's the condition. They must be at equilibrium. Then they should be able to form the size of a triangle where the length of the line is the magnitude and then the arrowhead shows the direction of the force, being a vector. So thank you. for listening. Please do well to go through the module and answer the questions. Thank you.